least one of these talks has in the past mentioned the signature idea from rough path theory. So in this talk, I'm gonna talk about it in hopefully some slower detail and why it's useful in a problem like Chinese character recognition. And I'll talk about some of the workflow that I'm using in my methods. So I'm gonna introduce the problem, I'll introduce signatures, and then maybe talk a bit more about the machine learning part of what I'm thinking about. So the type of handwriting recognition that I'm looking at is what is called online handwriting recognition. So someone has written a character with either a special pen or on a special touchpad or on a phone or whatever, so that available to the algorithm is not just the image of the character they've drawn, but the order in which they've drawn it, and speed and pressure and information might also be there, but I'm not using that in what I do at the moment. So here is the data set I'm using is actually being collected with one of these special pens, but the data set is basically, once you've learnt this, you can use it for touchpads or whatever. This is an example of the same single stroke Assamese character drawn by different writers collected in a similar data. So I'm working on Chinese, which is where characters have many strokes, up to say 20 or something. There are many characters. A basic data set has about 4,000 characters, but there are many more. I think here's an image of some characters from the homepage of this data set case here. So characters, there are official ways to write each character. So there are official orders to put the strokes down and orders which way round to draw each stroke, which there can be variation, but this information might as well be added if you have it to the process of classifying the character. So the basic problem that we're trying to learn is from samples, can we make a program which, given a new Chinese character which someone draws on their phone, we just identify which character it is. So it's a supervised machine learning problem, basically. Okay, so signatures. Rough path theory over the last 25 or so years, ideas from Terry Lyons and collaborators in Oxford he's answered questions in probability theory using a set of novel ideas that have become popular and famous in some quarters. I'm using the basic idea of signatures is a very special case where I'm using this concept, but I'm not using the full mathematical apparatus. So in his rough path theory, he cares about paths which could be arbitrarily rough or rough to a certain degree. So when you zoom into the paths, they still vary, like a fractal or worse or whatever. The path that you get out of a touchpad is a series of straight lines, and it's a small finite series of straight lines. So think 100 or something like that. So it doesn't have any of the mathematical nastiness that the theory was approached to think about. But on the other hand, this way to think about paths turns out to be useful. So if you think about the data in general in a machine learning problem, if you're trying to match a set of labels from a set of data, you will probably want to you might think about there being two steps. So a classification step is an algorithm that machine learning deals with. So it might, things like neural networks, support vector machines we heard about in the previous talk. We could be LDA, could be all sorts of things that machine learning does to extrapolate a function to new inputs. So these things are given samples of x's and labels, and they learn a function that should be good on more x's. But our input might not be the x's that we use. We'll choose a pre-processing step that might be a deterministic function or something that puts our input into some maybe fixed dimensional representation that we're going to use the machine learning classifier on. In the particular time-oriented thing, so let's say our data is a sequence of points in time or a sequence of some data at each time step. So a typical machine learning algorithm to use when the data looks like that is a recurrent neural network. And then our representation is going to be some function on each time step input to some R to the k for some real space. So I'm thinking of so for example, one thing you could do with characters, which turns out not to do very well in my experience, is that a Chinese character is a sequence of strokes, and your representation could be the length and the orientation of each stroke. So your input is all of that data. The represented input is going to be, for each stroke, its orientation and length or something. And then that can be fed into the recurrent neural net. So this is just a classifier that takes something that has a time dimension and uses that time dimension. So if you were to squash this into R to the big K, you'd lose. The classifier would have to learn afresh that, for example, a small translation in the time direction is not very meaningful, and that would be a waste of time for the classifier to have to learn. Okay, so what is a signature? So imagine a path. In this case, I'm looking at 3 dimensions. So what I think of a continuous path as a function from an interval to R to the d. So in this case, it's 3 dimensions. I'm mapping, say, 0, 1, the interval, with 3 functions. So these are the coordinate functions, f1, f2, and f3. So then the signature is the set of functions, is the set of numbers that you can get by computing iterated integrals. And they have, each element of the signature is indexed by a sequence of numbers from 1, 2, and 3. So for example, element 2, 3 of the signature, there are 2 numbers here, so it's going to be 2 integrals. And what are they going to be? They're going to be integrals of the derivatives of the functions I've been given with respect to t, iterated against each other. So I might write something like this, by which I'm sort of using the Steele-Tierney notation, but you can just think of it as this. So I integrate the derivative of f2 up to some index variable, and then I multiply it by the derivative of f3 of the same index variable and integrate that. So this inner one just evaluates to f2 of t. So you could think of this as f2 of t times f prime of t3. I can do this to any depth of iterated integrals. 2, 1, 2 will look like this. So I can flatten these out in a sequence by thinking about 1, 2, 3, 1, 1, 1, 2, 1, 3, and so on. Just so it's a sequence indexed by words on 1, 2, 3, but you can just think of it as a sequence. the first three elements are just going to be the total displacement of the path. So so element 1 of the signature is just f1 of 1 minus f1 of 0. The sort of information that you get from this is kind of hard to describe. Every element of the signature is affected by all values of t, kind of thing. So if I move a path a bit, in general, pretty much all of these values will change. I'll come back to this, but the second level kind of carries information about how much area the path has between it and the straight line connecting the endpoints. And I'll have a picture of this in a bit. So there are some nice theorems about this sequence of numbers and its relationship with a path, which kind of motivate this kind of thing. One is that up to a certain, if the path never goes exactly back on itself, which is called having a tree-like component, then in fact the signature is, then the mapping between paths and signatures is kind of one-to-one. So a path's signature will be the signature only of that path and not of any other path. If you go exactly back on yourself, that bit of the path is deleted. So in handwriting, people can't go exactly back on themselves, but you can also have, if a dimension never decreases, for example, you measure the time as well as where you are, then you never have the problem of tree-likeness. So I think of that as not being a worry. I can think of a signature as containing the same information as the original path. Also, these things are kind of, in a loose sense, these vary smoothly when this path varies. So a small change in a path produces a small change in these sequences, so that we'd like to think that major changes in a path could be meaningful in handwriting. So like there's a big difference between a T and an S, but between my S and your S, hopefully that difference is going to be small. And so hopefully looking at signatures should be a natural thing to do, to want to do in a problem like handwriting. So how big is, so a signature is an infinite series. I can't send an infinite series. My k on the previous slide had to be a finite number. So I'm going to stop after some depth, which I'll call my level, and I'm usually going to use the letter m for that. So level m of the signature is all sequences of the d numbers of length m. So it has d to the m values. And we think of it as taking values in r to the d tensored m. So calculating the signature, evaluating the integrals on a given path where the path is specified as a series of line segments is very easy, using a formula called Chen's identity. So it turns out that the information in the first m levels of the signature is slightly superfluous. So if I give you element 1, you know element 1, 1 just by iteration, just by sort of like an iteration by parts argument. So if I want to compress this information, there is a natural compression called the log signature, which is much smaller. So for example, if in 2 dimensions up to level 4, there are 30 numbers, so that's 2 plus 2 to the 2 plus 2 to the 3 plus 2 to the 4 is 30. But actually there's only 8 numbers worth of information in that. Now, I'm going to use this case for a demonstration because 8 is quite convenient. If my path is made of 4 line segments in 2D, that gives me 8 degrees of freedom. So that means if I work on the set of paths made of 4 line segments, I sort of have a nice one-to-one mapping between that and the first 4 levels of signature. So I have a little demonstration of what these things look like. Let me explain what we're seeing. Does my mouse show up? Yes. Okay, so I have a path over here made of 4 segments, and on the right I have, if you don't worry about the bottom, there are these widget sliders and 2-dimensional widgets that represent the value of the signature of the path on the left. So I can do 2 things. I can move points on the left and you'll see the widgets move, and I can also solve and hopefully move the widgets and you'll see how the path moves. So I mentioned that, for example, that level 1 is the total displacement of the path. So if I move the endpoint around to the right, you'll see that the level 1, this thing over here, moves as I move the mouse. So moving it left, moves it left, moving it up, moves it up, and so on. The others also move. This level 2, there's only one number in this compressed representation, and like I said, that's the area between this straight line and the path that I've been given. So if I increase that area, you will see that number move to the right. The movement of all the other widgets is slightly difficult to understand. These ones are going to be more asymmetrical in whether they care about the beginnings or ends of the path. So it turns out level 3 is 2-dimensional. I can represent it as a plane, point in a little plane, and there's 3D in the 4th level. What I can do, hopefully, is go backwards so that I can move these and you'll see how the path moves. And this is just running with a numerical solver. Inverting a signature is a project that another Alan Turing student is working on, and it's quite hard. And this is just a crude numerical solution to the problem, which shows it is a bit intuitive. So hopefully, when I reduce the area, you'll see the path come closer to a straight line, and but the endpoint stay fixed because level 1 is fixed. Moving other elements higher levels, you'll see slight changes in the path, but it's quite difficult to understand what they're doing. So yeah, so smooth changes to any of the widgets on the right map to smooth changes to all the points on the left in a way, in a smooth way. But it's for the higher ones, it's quite difficult to explain how that works. But hopefully that gives you a feel for the signature as a summary of a little path. Let me go back to my slides. So some questions about using the signature in a machine learning setup like this might be, so how many levels should I use? I mentioned that using whole strokes is not optimal. It seems to be that you want to cut up strokes into small pieces and send them to a recurrent neural network or similar to learn effectively. So there is a question of how much you should balance more information in the signature versus more computing power in your recurrent neural net. And yeah, so where to chop up, how small the bits should be, that kind of thing. So my aim is not just accuracy. I want the whole process to learn quickly. So the state-of-the-art apps for iOS and Android phones actually do use signatures. They use signatures, but they use a much more complicated machine learning architecture than the one I've talked about, if I understand correctly. So I think it's GPen, these researchers in South China University, their model takes days to train. So it takes the examples from a data set, and it has a lot of parameters and a lot of neural network power. So part of what I'm looking at is trying to be clever about the way we design the machine learning and take our input to it so that it learns. So the best examples I've got learn in a few hours. They don't get super accuracy, but they get like reasonable accuracy. In the 90% accuracy on 4,000 characters. So maybe I'll say a bit more about recurrent neural networks. So a simple single layer recurrent neural network takes, so our input is r to the d times time. So basically we learn a function which is just a matrix multiply times some nonlinear function, typically the positive part function, which is called ReLU in this context. So that learns a new state from a new state and potentially an output from an old state and an input. So this function, so you then think about composing this for every t, and you have a big function that multiplies data by a matrix and has lots of these nonlinearities to get a state to a final state, which we're going to take as an output, as a to use in the next stage of our classifier, maybe a simple neural network or something. So neural networks in general are functions are highly parameterized, flexible functions, and they learn. Some things are easier to learn by them than others, but by combining layers of these things, for example, they can learn quite complex things. When t is long, there's a problem about these things not remembering much about input 1 when they're at input 100, which another architecture called long short-term memory, which I'm not going to talk much about, addresses. So it has more, it sort of augments state with states that's hopefully more slowly varying across t. So I use this or long short-term memory as my classifier, and there's some questions about whether you could have some state stored in the signature way, which I'm thinking about at the moment, but not going to say much more about. This is the shape of an LSTM, but actually, okay, I have more time than I thought. I will say more about this. In general, that's what I've got working best for a quick learning of Chinese characters, just using LSTM with clever cutting up of characters. So, okay, I will say a bit more about LSTM then. So LSTM is based, again, think about this as the time I've borrowed this diagram. There's memory that is that works just like the standard recurrent neural net memory. So it goes through, at every time step, it's gone through a matrix multiplication. But there's also a state that's only been multiplied by something that's like 0 or 1 and added to by something that's basically like 0 or 1. So this sigma is a function like that maps a real line onto 0, 1 symmetrically. An arctan is the other, hyperbolic tan is another nonlinearity that maps onto -1, 1. The the idea would be that this this saves our this saves the what's called vanishing or exploding gradients, because this thing is about 1 or 0 and stays always about 1 or 0. It doesn't. It can sort of be on or off, lasting for a long time. And obviously, when I say 1 or 0, I really mean a vector of them. So this is just an example of one unit. So the idea would be that a signature as well is something that we know how to join things onto using the same Chen's formula that I mentioned earlier, and we can collapse down. So maybe instead of a 1 or a 0, we could use some of the same properties to make a memory unit in one of these that might be a bit more powerful than a 1 or a 0. So you'd have something like a signature here and something like a normal set of numbers here. Yeah, so that's just another thing I've been thinking about. So thank you. And here I've been working with Ben Graham, who was my supervisor and is now working for Facebook AI. And thank you to the Turing and Warwick and EPSEC. Thank you very much.